February 14th, 1945. Deep beneath the scarred streets of Berlin, in a concrete bunker 40 feet underground, Chief Engineer Otto Kramer pressed his ear against the housing of a massive electric motor. The thrumming vibration told him everything he needed to know. They had maybe 6 hours before complete failure. Above him, the conveyor belts of the Siemens underground factory continued their relentless march, feeding components to assembly lines producing electrical equipment for U-boats, aircraft, and anti-aircraft batteries. But Kramer knew what the plant managers didn't. Without this motor, without the dozen others like it scattered throughout Berlin's subterranean manufacturing network, the entire production line would grind to a halt. And in February 1945, with Soviet forces less than 50 miles from the city, every hour of production mattered. The problem wasn't the motor itself. German engineering was still world-class, even as the Third Reich crumbled around them. The problem was inside the motor, in a component so small, so seemingly insignificant, that most people had never heard of it. The carbon brush, or rather what should have been a carbon brush, but in Germany's case by 1944 had become something else entirely. Something desperate, something that was slowly killing every electric motor in the Reich. Kramer wiped the sweat from his forehead despite the February cold. He'd been an electrical engineer for 23 years, had worked on some of the most advanced electrical systems in Europe, but nothing in his training had prepared him for this, for trying to keep an industrial empire running when the most basic materials had simply vanished. To understand how Germany arrived at this crisis, we need to go back 3 years earlier, to a time when the war still seemed winnable, when the factories hummed with confidence, and when nobody was worried about something as mundane as graphite. 1942 was the year everything changed, though few realized it at the time. That was the year Allied bombing campaigns began targeting not just German factories, but the supply chains that fed them. And one of those supply chains stretched all the way to Ceylon, modern-day Sri Lanka, where the British controlled vast deposits of high-quality graphite. Before the war, Germany had imported over 60% of its industrial graphite from British Commonwealth sources. By late 1942, that number was 0. Now, you might be wondering, what's so special about graphite? Why would the lack of this one material matter so much? Let me paint you a picture. Every electric motor, from the tiny ones in fire control systems to the massive industrial motors driving factory equipment, relies on carbon brushes. These brushes are spring-loaded contacts that press against rotating commutators, transferring electrical current while the motor spins. Think of them like the connection point between stationary and moving parts, constantly making and breaking contact thousands of times per second. Graphite was perfect for this job. It conducted electricity beautifully, it was self-lubricating, and it wore down slowly and predictably. A good graphite brush could last for months, even in heavy industrial use, but more importantly, graphite was soft enough that when it did wear down, it wouldn't damage the copper commutator it pressed against. This was the key. The brush was sacrificial, designed to wear out so the much more expensive, much harder to replace, commutator would survive. In the sprawling industrial complex of Krupp in Essen, master mechanic Heinrich Müller first noticed the problem in March of 1943. He'd been maintaining the electric motors that drove the massive lathes and milling machines in the armaments factory for 15 years. He knew the sound of a healthy motor the way a doctor knows a healthy heartbeat. And on that grey March morning, walking through the factory floor, he heard something wrong. Motor number 47, a 50-horsepower beast that drove 3 heavy lathes simultaneously, had developed a grinding noise. Not the usual hum, not even the squealing that indicated a brush needed replacement. This was deeper, more ominous. When Müller shut down the motor and opened the brush housing, he found something that made his stomach drop. The copper commutator, the cylindrical switching mechanism that should have been smooth and golden, was scored with deep grooves. In some places, the copper had been worn away completely, exposing the iron core beneath. This shouldn't have been possible. Commutators were designed to outlast the motors themselves. Müller had seen motors run for 20 years without needing commutator replacement. This one had been rebuilt just 8 months ago. He pulled out the brushes and immediately understood. They weren't graphite, they were copper. Solid copper, harder than the commutator itself, and they'd been grinding the commutator down like a file. What Müller didn't know, what couldn't know from his position on the factory floor, was that this wasn't an isolated incident. It was happening in every major industrial center in Germany. It was happening in aircraft factories in Bavaria, in submarine yards in Bremen, in chemical plants in the Ruhr Valley. The Reich's entire industrial infrastructure was slowly being eaten alive from the inside, one motor at a time. The decision to switch from graphite to copper brushes hadn't been made lightly. In Berlin, in the austere offices of the Reich Ministry of Armaments and War Production, a young engineer named Werner Osenberg had been given an impossible task in late 1943. Albert Speer himself, Hitler's architect turned armaments minister, had made it clear. Production must not stop. The factories must run. Find a solution to the graphite shortage, and find it now. Osenberg and his team had considered every alternative. They'd looked into synthetic graphite, but the production process required enormous amounts of electrical power and specialized equipment, resources that were already stretched impossibly thin. They'd investigated importing graphite from neutral countries, but the prices were astronomical and the supply was unreliable. They'd even experimented with organic materials, trying to create carbon brushes from compressed coal dust or petroleum byproducts. Nothing worked well enough, fast enough. That's when someone suggested copper. It seemed insane at first. Copper was harder than graphite, much harder. It would wear down the commutators rapidly, but copper was available. Germany had copper mines in Saxony, had stockpiles, had recycling programs, and crucially, a motor with copper brushes would run. It might not run for long, but it would run. In the calculus of total war, that was enough. By January 1944, the switchover was official. Ministry directives went out to every major factory: conserve remaining graphite stocks for critical applications only. Aircraft generators, fire control systems, communications equipment, everything else would use copper brushes. The engineers who received these orders knew what it meant. They were being told to sacrifice long-term reliability for short-term production. They were being told to burn through Germany's industrial infrastructure to keep the war machine running just a little bit longer. And that's exactly what happened. At the Daimler-Benz factory in Stuttgart, production supervisor Karl Hoffmann watched his motor replacement rate triple between March and June of 1944. Motors that should have run for years were failing after months. Some lasted only weeks. Each failure meant hours of downtime, meant workers standing idle, meant production targets missed. But the alternative was worse. The alternative was stopping completely. The copper brush problem created a cascading series of crises that rippled through German industry in ways the planners in Berlin hadn't anticipated. When a motor failed, it wasn't just a matter of replacing the brushes. The damaged commutators had to be resurfaced, a delicate machining operation that required skilled labor and specialized tools. In many cases, the damage was so severe that the entire motor had to be rebuilt or replaced. And motors weren't simple to replace. A large industrial motor could weigh several tons, required precise installation, and needed to be carefully balanced and aligned. By the summer of 1944, Germany faced an absurd situation. They had factories full of working machinery, but the motors driving that machinery were failing faster than they could be repaired. They had trained workers, raw materials, even some remaining design expertise. But they couldn't keep the lights on, couldn't keep the conveyor belts moving, because they'd run out of a material that most people had never heard of. Let me give you some numbers to understand the scale of this crisis. A typical German armaments factory in 1944 might have between 200 and 500 electric motors of various sizes. Before the graphite shortage, the average motor required brush replacement every 4 to 6 months and commutator servicing every 3 to 5 years. With copper brushes, those numbers changed dramatically. Brushes now needed replacement every 2 to 4 weeks, and commutators needed resurfacing every 3 to 6 months. The maintenance burden increased by a factor of 10 or more. The Krupp works in Essen, one of Germany's largest industrial complexes, employed over 600 maintenance electricians in early 1944. By September, that number had grown to over 1,000, and they still couldn't keep up. Workers were being pulled from production lines to help with motor maintenance. Engineers who should have been designing new weapon systems were instead trying to figure out how to extend the life of copper brushes by even a few days. But here's where the story takes an even darker turn. Because while German engineers struggled with copper brushes in their factories, German soldiers were facing the same problem in the field, often with lethal consequences. Electric motors weren't just in factories, they were in tanks, in aircraft, in submarines. They powered gun turrets, fire control systems, hydraulic pumps, and all of them were failing. On June 8, 1944, 2 days after D-Day, Oberleutnant Friedrich Weber commanded a Panther tank in the 21st Panzer Division near Caen. His tank was relatively new, built just 4 months earlier in the Mann factory in Nuremberg. It should have been one of Germany's most formidable weapons. The Panther's 75mm gun could destroy any Allied tank at range, and its sloped armour made it nearly invulnerable from the front. But on that June morning, as Weber's tank moved into position to counter-attack against British forces, the electric motor that powered his turret traverse system failed. The turret, which should have been able to rotate a full 360 degrees in under a minute, locked in place. Weber's tank, with its powerful gun and thick armour, became essentially useless. It could only fire at targets directly in front of it. When British Cromwell tanks manoeuvred to its flanks, Weber couldn't respond. His tank was knocked out not by superior Allied technology, but by a worn-out copper brush in a motor that should have been fitted with graphite. This wasn't an isolated incident. Tank maintenance reports from the summer of 1944 show electrical system failures becoming increasingly common. The Tiger II, Germany's most powerful tank, was particularly vulnerable. Its massive turret required electric motors to traverse, and the copper brushes in these motors wore out so quickly that some crews reported failures after just a few hours of operation. In the air, the situation was equally dire. The Focke-Wulf FW-190, one of Germany's premier fighter aircraft, used electric motors for everything from landing gear operation to gun charging mechanisms. Pilots began reporting electrical failures with alarming frequency. On August 12, 1944, Lieutenant Hans Müller, no relation to the mechanic in Essen, was flying escort for German bombers over France when his FW-19's electrical system failed completely. His landing gear wouldn't deploy, his gun charging system was dead, even his radio went silent. He managed to belly land the aircraft, but dozens of other pilots weren't so lucky. Beneath the waves, the problem was perhaps most critical of all. German U-boats relied heavily on electric motors, not just for propulsion when submerged, but for air circulation, for periscope operation, for hydraulic systems. The Type 21 U-boat, Germany's revolutionary new submarine design that entered service in 1944, was supposed to be the weapon that would turn the tide in the Battle of the Atlantic. It could travel underwater faster than most surface ships, could stay submerged for days, was nearly silent. But its advanced systems required dozens of electric motors, all fitted with copper brushes. Captain Lieutenant Adalbert Schnee, commanding U-2511, one of the first Type 21 boats to become operational, wrote in his war diary about the constant electrical problems that plagued his supposedly superior submarine. On what should have been a routine patrol in April 1945, 3 separate motor failures forced him to surface in hostile waters, risking detection and attack. The Type 21 was technologically advanced in almost every way, but it was crippled by something as simple as inadequate motor brushes. Back in the factories, engineers were desperately trying to find solutions. Some attempted to create hybrid brushes, mixing copper with whatever carbon materials they could scavenge. Coal dust, lamp black, even ground-up pencil lead was tried. Others attempted to redesign motors to reduce brush wear, adding additional lubrication systems or modifying the spring tension to reduce contact pressure. A few even tried to return to older brushless motor designs, though these were inefficient and unsuitable for most applications. At the Siemens Research Laboratories in Berlin, a team led by Dr. Hermann Landau made perhaps the most interesting breakthrough. They discovered that by plating copper brushes with a thin layer of silver, they could reduce wear significantly. Silver was softer than copper, but harder than graphite, a middle ground that extended motor life considerably. But silver, like graphite, was in critically short supply. The silver plating solution, while technically elegant, was economically and logistically impossible to implement on a large scale. Some factories got creative with maintenance schedules. At the Messerschmitt plant in Regensburg, Supervisor Otto Brandt implemented a rotating shutdown system. Different sections of the factory would shut down for motor maintenance on different days, allowing continuous production at reduced capacity rather than catastrophic failures that would halt everything. It was inefficient, it reduced overall output, but it kept the factory running. By late 1944, the copper brush crisis had become so severe that it was affecting strategic planning. When Albert Speer presented production forecasts to Hitler, he had to account for increasing motor failures. Tank production wasn't limited by steel availability or labor shortages or bombing damage, at least not entirely. It was limited by how many motors could be kept running in the factories. Aircraft production faced the same constraints. Even ammunition production was affected as the electric motors driving shell presses and powder mixers wore out faster than they could be replaced. If you're wondering how the Allies knew about this problem, the answer is they didn't, not fully. Intelligence reports noted increasing German electrical failures, but the specific cause, the lack of graphite and the forced substitution with copper brushes, wasn't clearly understood until after the war. If it had been, Allied bombers might have prioritized motor manufacturing facilities even more heavily. As it was, they were already doing enough damage. The bombing campaign against German industry in 1944 and 1945 was devastating, but the copper brush problem made it exponentially worse. When a factory was hit by bombs and suffered damage, repairing the structural damage was often faster than getting the electrical systems back online. Bombed buildings could be cleared and rebuilt relatively quickly. Damaged motors, especially those already worn down by copper brushes, were often beyond repair. Let me take you back to where we started, to Otto Kramer in that Berlin bunker in February 1945. The motor he was listening to that day powered the main assembly line for electrical components. It was a massive 200 horsepower motor, built in 1937, that had run nearly continuously for 8 years. Before the copper brush conversion, it might have run for another 8. Now, after 16 months of operation with copper brushes, it was dying. Kramer had already replaced the brushes 11 times. He'd resurfaced the commutator 4 times. But there was a limit to how much copper you could remove from a commutator before it became structurally unsound. This motor was at that limit. The next failure would be catastrophic, would likely destroy the commutator completely and possibly damage the armature windings. There was no replacement available. The factory that had built this motor, Siemens's main plant in Munich, had been bombed into rubble 6 months earlier. Kramer made a decision that day that probably saved the factory, at least for a few more weeks. He shut down the motor voluntarily before it could fail catastrophically. He redistributed the load across 4 smaller motors, overloading each of them but spreading the risk. Production dropped by 30%, but production didn't stop. In the calculus of February 1945, that counted as a win. But across Germany, hundreds of other engineers were facing similar decisions, and not all of them ended as well. At the Henschel tank factory in Kassel, a motor failure in January 1945 caused a fire that destroyed an entire assembly building. At the Junkers aircraft plant in Dessau, cascading motor failures brought production to a complete halt for 3 weeks in March. At countless smaller facilities, the lack of reliable electric power simply forced closures. When the war ended in May 1945, Allied technical intelligence teams fanned out across defeated Germany, cataloguing weapons systems, interviewing engineers, seizing documents. What they found in the factories surprised them. The machinery itself was often in better condition than expected. German manufacturing equipment was world-class, well-maintained despite the bombing. But the electric motors were destroyed, not by bombs, not by sabotage, but by copper brushes grinding away at copper commutators, month after month, until there was nothing left. In post-war reports, American and British engineers calculated that the graphite shortage and the forced substitution with copper brushes had reduced German industrial capacity by at least 20 to 30%, possibly more. That's not counting the indirect effects, the wasted labour on motor maintenance, the production delays, the weapon system failures in combat. Some historians have argued that the copper brush crisis shortened the war by months, that Germany's industrial base would have lasted significantly longer if they'd maintained access to graphite supplies. The irony, of course, is that graphite isn't particularly rare. It's not like uranium or platinum or some exotic material that exists in only a few places. There are graphite deposits all over the world. But in 1944, Germany couldn't access them. They were cut off from international trade, their allies couldn't supply them, and their synthetic production capacity was overwhelmed. So they used copper, and they ground their industrial infrastructure down to nothing. Today, if you visit the Deutsches Museum in Munich, there's a small exhibit on wartime manufacturing. Among the displays of aircraft engines and tank components, there's a glass case containing 2 motor brushes. One is graphite, smooth and black, showing minimal wear despite years of use. The other is copper, deeply scored and pitted, worn down to half its original size after just a few months. The placard is simple: the difference between peace and war. The story of Germany's copper brush crisis is a reminder that wars aren't just won and lost on battlefields. They're won and lost in factories, in supply chains, in the availability of materials so mundane that most people never think about them. A soldier can be brave, a tank can be well designed, a strategic plan can be brilliant, but if the motor that traverses the turret fails because someone used the wrong material in a brush, none of that matters. Otto Kramer survived the war. He was captured by Soviet forces when Berlin fell and spent 3 years in a prison camp before returning to West Germany. He never worked as an engineer again. The trauma of those final months of watching Germany's industrial capacity crumble from the inside had broken something in him. But in interviews late in his life, he would talk about the copper brushes, about the impossible task of keeping motors running with inadequate materials, about the grinding sound that haunted his dreams. Heinrich Müller, the mechanic in Essen who first noticed the problem, also survived. He emigrated to America in 1951 and found work maintaining industrial motors in a steel mill in Pittsburgh. He was known for his almost obsessive attention to brush quality, for his insistence on regular maintenance, for the way he would press his ear against a motor housing and listen. His co-workers thought he was eccentric. They didn't know what he'd seen, what he'd lived through, what he understood about the fragility of industrial systems. If there's a lesson in all of this, it's about the interconnected nature of modern warfare, about how the lack of one seemingly insignificant material can cascade through an entire industrial economy. Germany in 1944 had tanks and aircraft and submarines. They had steel and aluminum and fuel, at least in limited quantities. They had skilled workers and experienced engineers. What they didn't have was graphite, and that lack of graphite, that forced substitution of copper for carbon in millions of motor brushes across thousands of factories, helped bring down an empire. The next time you flip a light switch or start a car or use any device with an electric motor, somewhere inside that device is probably a carbon brush, quietly making contact, conducting current, wearing down slowly and predictably. It's a small component, easily overlooked, but without it, our entire electric civilization would grind to a halt. Germany learned that lesson the hard way, in factories and tanks and submarines, in the grinding sound of copper on copper, in the darkness of failed motors and failed ambitions. And if you found this story fascinating, if you learned something about the hidden infrastructure of warfare, about the small details that determine the outcome of history, do me a favor and hit that like button. Share this video with someone who appreciates the engineering side of history. because these stories, these technical tales of desperate improvisation and inevitable failure, they're just as important as the battles and the generals and the famous dates. They're the stories that explain how things actually happened, why victories occurred and defeats became inevitable, and there are hundreds more stories like this waiting to be told.